Welcome to Micro Communication course. So today we start a new topic, micro measurement here. So in a micro measurement, what are the various devices used? What are the various micro devices are used? That we will learn. And for the micro measurement, which components supposed to be considered? Okay, for measuring the a measurement done at a micro frequency. Generally, whenever we are working at a micro frequencies, so some parameters are important, and that parameters to be measured or parameters we should know that. Okay, that values of those parameters we should know. So in that case, for the micro measurement we supposed to know that what is the frequency there. Okay, that is about the one parameter. We supposed to know that what will be the frequency. Then we supposed to know that what will be the a guide wavelength here. Okay, then we supposed to know that what will be the standing wave ratio. Then what will be the impedance here. Then what will be the power, and then what will be the alternate. Now these are the various micro parameters. Whenever we use any micro circuit, so in that case at a micro frequencies, so what are the various parameters, and that parameters we supposed to measure it. Okay, in any circuit. So that parameters are nothing but a frequency. What is the frequency of your signal to be propagating through the guide? What will be the guide wavelength there for the given dimension there? So what will be the standing wave ratio? What will be the impedance here for your signal or for your device? Okay, so we supposed to consider that any device, so there will be some impedance, or supposed to how your signal is propagating through the signal to the alpha through the guide. So what will be the power here? The minimum power or maximum power we supposed to use at a in the given particular guide. Then how much is the attenuation there takes place if we insert any component in between? Then what are the various components? So in a micro measurement, we supposed to measure these particular parameters at a micro frequency. Okay, so any circuits, those are working at a micro frequency. For those micro circuit, we supposed to measure this particular a parameter there. So now to measure this particular parameter in a lab, okay, laboratory here, in that case we supposed to use a multiple device setup, and that multiple device setup is supposed to called as a micro bench. Okay, so what are the various components present in the micro bench? So micro bench generally it is to be used in a laboratory. It has a, a source. Okay, so it's supposed to consider that what are the various components. So it has a source. Then we can say that a alternator, then a frequency meter, then a tunable probe, and all these are the components of a micro bench. And these micro bench components supposed to be used to measure the micro parameters. So that parameters we have seen earlier, that frequency, guide wavelength, standing wave ratio, then a impedance, then power, then attenuation. Now these are supposed to be measure. These are supposed to be a parameter measured through the microwave measurement technique. And for a microwave bench in a lab, these are the components present in the given particular bench. So now that microwave bench is to work at a what frequency, or what will be the other parameters that is to be measured here. So generally in a lab, that microwave bench is a rectangular waveguide, means all other components they consist of a rectangular waveguide, and that all other components are connected to the microwave, connected each other there to measure the microwave parameter. So now to understand that a microwave bench, suppose we should know that what are the various features of this microwave bench. So if supposed to be we are using a rectangular waveguide, then for the rectangular waveguide, what will be the mode and what will be the frequency band of a operation there. So we should know that a microwave bench we supposed to use in a lab. What are the salient features? Generally, it has a range of the frequency that is to be operating. So we supposed to know that what will be the frequency band of a operation. So generally, it is about a X band here. Okay, so band we say that a X band, and that frequency ranges is from the 8 to 12 gigahertz. So we write exactly what will be the frequency for the given particular band. So that will be of a 12.4 a gigahertz. So generally we say that 8 to 12 gigahertz approximately we say for the given particular band. And then this one is about a frequency we say. And what will be the wavelength? So wavelength is about what? A 3.66 to 2.42 centimeter. Okay, that is about a wavelength here. So what will be the wavelength? Okay, and because we supposed to calculate that for a given particular band, a wavelength here. Okay, so in this case, we should know that what will be the a frequency band of a operation for the given particular microwave bench. Then for the measurement, we supposed to know that what is the mode of wave. Okay, we say that wave is propagating through the guide. So what will be the mode of a wave? Generally, in a lab, we consider that a TE10 mode. Okay, we supposed to consider that a TE10 mode, and for this T10 mode, it is nothing but a dominant mode. So then for the dominant mode, a cutoff wavelength is supposed to be a twice A. Okay, so then that A is nothing but what? For a rectangular waveguide, this is supposed to be a rectangular waveguide we say here. So this one is about the inner dimension of a guide. Okay, so whatever the inner dimension of the guide is nothing but the A here. Okay, so for a rectangular waveguide, this one is about the inner dimension. So a cutoff wavelength for a T10 mode, generally it is say that lambda c is equal to twice of it. You just remember always. Okay. So that is about A is nothing but what? That is about the inner dimension. Or we can say that inner width, okay, of this waveguide then. Or we can say that distance between the a two side walls. These are nothing but a side walls here. The distance between the a two side wall. So that is nothing but the A here. So lambda c we will calculate, that is about lambda c is equal to a twice of A here. Then what are the dimensions of a guide? So for a given particular bench, the dimensions are important. Okay. So we supposed to know that the dimensions of a guide. Okay, dimensions of a guides are nothing but what we can say A into B. Okay, I write here the dimension of a waveguide. Okay, that is about A into B. So what is the value of A and a B here? So we say that A is equal to what? A 2.286 into 1.016 a centimeter. Okay, that is about a dimension of a waveguide. And then a guide wavelength range. Then a guide wavelength range, that is about a 2.85 to 6.11 centimeter. That is about a guide wavelength range. Now this one is about we say a dimension of a guide, and we say that this one is about a guide wavelength. So now for a given particular guide, there should be some cutoff frequency or there should be some cutoff wavelength. So at this particular dimension, okay, at the given particular dimension, we say that a cutoff frequency as well as a cutoff wavelength. Cutoff wavelength, or we say a cutoff frequency here for a given particular guide is about a 6.56 gigahertz. That is about a cutoff frequency, and a cutoff wavelength is about a 4.57 centimeter. because we say that a T10 mode lambda c is equal to twice of a. So what will be the cutoff wavelength? Okay, so for a given dimension, this one is about a dimension of a guide. For a given dimension, so it has a cutoff frequency of a 4.57 centimeter as well as a cutoff frequency is about a 6.56 gigahertz. That is about a given rectangular waveguide. Where for which rectangular waveguide? So the dimensions are nothing but a 2.286. Okay. So why this one is about a cross? Because this one is about, we say it is about a here. Okay. So that's why A belongs to this one, and this one is about a, what we can say, it is about a B here. And these are nothing but the, what you can say, the guide value. So dimensions of a guide, add this particular A into B here. A is what, 2.286 into what, that B is about a 1.016 centimeter. That is, these are the dimensions for what your guide will work. Okay, that is about a dimension. And for this given dimension, so cutoff wavelength and a cutoff frequency here it is given. So cutoff frequency for a given dimension, that is 6.56 gigahertz, and wavelength is about a 4.57 a centimeter. Now these are the salient features of a rectangular waveguide that we are used in a laboratory for the microwave measurement purpose. Okay, so now we should know that for a given particular rectangular waveguide, so that blocks we say earlier. Okay, what are the various blocks? Okay, for the microwave measurement. So in that case, we supposed to know that what are the various microwave bench components. Okay, so what are the various blocks of the microwave bench? Okay, so what are the various blocks? Okay, of microwave bench. Okay, that bench is, why it is called as a bench? Bench is used, that is about a word. Okay, microwave bench, because in a laboratory to measure the microwave parameters, we're supposed to set a devices. Okay, we are supposed to set a multiple devices, and that multiple devices are used to measure the microwave parameter. And that set, multiple set of a devices arrangement here, and that particular arrangement for the measurement in a laboratory, that is called as a microwave bench. Okay, and what are the blocks of the microwave? Okay, so now we learn that what are the various blocks of the microwave bench. So generally we say that here it has a source. Okay, so we supposed to write, or we supposed to draw a blocks. So likewise, generally we say that initially we supposed to be a source here. So then what type of a source supposed to be used here? Okay, that source can be of a klystron. Okay, source can be of any other device. We say that for a microwave bench, okay, in a laboratory measurement, we use a reflex klystron as a microwave source. Okay, so in a laboratory, we're supposed to use a reflex klystron. Why reflex klystron? Because it provides a modulated signal, and that modulated signal of a 1 kilohertz signal. Okay, that it modulate a 1 kilohertz of a signal there. So that we'll get the output across the detector, that 1 kilohertz signal. Okay, so we'll see in detail what are the various bands supposed to use. Or we can use, instead of that my reflex klystron, we can use a gun oscillator. Okay, so in that case, we supposed to modulate the signal using a pin modulator. Okay, so we have a source. If it is a reflex klystron, the signal get modulated here inside the klystron, there reflex klystron, that is about a 1 kilohertz signal. If supposed to be we are using a gun oscillator as a microwave source, then we supposed to use a pin modulator to modulate the signal. Okay, so modulation takes so that your 1 kilohertz 1 kilohertz signal is transmitted. Okay, then then another component is about what, a isolator. Okay, another block measurement here is about a isolator. So now the role of the isolator here is, so if supposed to be any other components are there now. Okay, here we have a lot of components. and supposed to be any mismatch occurs at this particular component or at the load, then what happen? Reflection will occur, and that signal will be reflected toward the source there. Okay, to avoid that, okay, that reflected signal to reach to the source, a device is used that is about a isolator. The role of isolator is about it transmit the signal, it allow the signal only in a given direction. So now this one is about a direction. So it's not allow the signal backward. Okay, if supposed to be that reflected signal reach to the source, then our source may get damaged. So to avoid it, so we supposed to use a isolator here. So it is nothing but what that isolator is nothing but it keeps or it makes an isolation between your load and a source here. That is about your isolator. So okay, so means any reflected signal or any back signal will not be entered to the source or will not be reached to the a source here. So that is about what we can say a isolator here. Then another block, a alternator. Okay, now the role of a alternator here in the given particular setup to set the particular level of a output power. Okay, so how much is the power required, okay, to be transmitted so that your device or at the end detector we have that detector able to read the whatever the power is transmitted. If supposed to be power is large, then our detector will damage or device at the receiver will damage. Okay, so in that case we supposed to use the alternator so that that will limit the power, okay, that will reach to the it whatever the detector there. So detector can be anyone. So we'll see that detector one by one here. So okay, so here the role of the alternator, it will limit the whatever the output power of the device or output power of the base to be measured. So generally there are the two types of alternator. One is about variable alternator and one is about a fixed alternator. But mostly in the case of a micro bench, that variable alternator is to be used. Okay, because we can limit the power in the category particular power level value. Okay, for through this alternation. So flap alternator, or we supposed to use a fixed alternator. We supposed to use a variable alternator. Okay, that is about the another band, another component. Then we supposed to know that what signal is to be transmitted through the device. So that's why we should know that what is the frequency of the microwave signal. So that's why we supposed to use a wave meter. Now wave meter, okay. So wave meter is nothing but what? A device that will measure the a frequency of a microwave signal. Signal means what? This one is about a source. The source is generating microwave signal. That microwave signal, what is the microwave signal frequency that can be measured through the wave meter. So we say earlier a frequency meter because it has a signal and signal is supposed to be measured. Okay, okay, whatever the frequency of that given signal is to be measured. So instead of that here, in a guide, wave is propagating. So that's why that meter is called as a wave meter. Okay, so that because that guide if we have through the guide, the signal is transmitted in the form of a wave. Okay, so whatever the rectangular components we are using here that are transmitting a wave. Okay, your signal will be transmitted in the form of wave. So that's why the measurement is to be done based on the wave here. So that's why the name is called as a wave meter. So the role of the wave meter here is to measure the whatever the microwave frequency propagating through the guide here. So generally here we say that X band of a okay signal uh, is propagating through the microwave. So X band means what? 8 to 12 gigahertz. And we already know that source here. Okay, so source will work or source will operate within the given particular band that is about a 8 to 12 gigahertz. So now then wave meter will be operating in the given particular range that is about a 8 gigahertz to a 12 gigahertz. So it will measure the frequency directly. Okay. So now that is about a wave meter. So now what are the components in the wave meter here? So generally there are the two types of a wave meter. One is about a direct measurement type. Okay. So it will measure the direct the whatever the frequency of the signal there, and it will display on the a display device. That is about we can say that a direct measurement type. Okay, so we can say that, or another one is about what we can say here, a indirect measurement. So in that indirect measurement, we supposed to calculate that at what particular resonating frequency we will get the deep across the detector there. Okay, at the detector. So in that case, that will be of a indirect one. And direct, okay, so there, so in a direct one, there are the two types. One is automatically display the values on the display, or another direct type method measurement is about we supposed to find out the depth at the well, uh, at the load there, or at the detector. So now how this wave meter will be looks like. So generally, a wave meter it has some sliding, okay, screw is there. Okay, so we supposed to consider that how your wave meter will be looks like. Okay, so now here there is some small plunger here, and this one we supposed to use to rotate this device here. Okay, so whenever we are rotating, okay, whenever we are rotating here, and then okay, now this one is about a we have a waveguide now. Okay, so now your meter is mounted that cavity. Okay, this device is mounted on the guide here. Okay, so generally it is on the guide. So now here the small opening on this guide is there. Okay, that is at the center. Okay, so generally I have to draw here instead of a guide here. So I supposed to draw likewise. Okay, so we supposed to consider that this one is about a waveguide now. So there is a small section that is about a cavity. Through that cavity, whatever the signal is propagating here, okay, that is about your input signal we say here, and here we'll get that a output now. So whichever the signal is propagating there, that will be moved toward this a cavity there. Okay, here there is a small opening inside this particular device, and this cavity size will be increasing using or decreasing using this a plunger. So we're supposed to rotate this plunger here so that this plunger will come down or up. Okay, there are the two directions of this particular plunger here, up or down here. Okay, while we are moving. So according to that, this cavity size will change. Okay, now there will be change in the cavity size because of that movement of the plunger there. If the cavity size change, then resonating frequency of the cavity changes. Okay, now we supposed to consider that in general, whatever the waveguide we have, signal is supposed to be propagating and will get the out here. That is about a rectangular waveguide. But one device is there that is about a meter is present on the guide. Okay, so likewise here, so it has some particular cavity. And now when signal is propagating through the cavity, okay, here, whatever we can say that this one is about a rectangular waveguide. That's one setup. Your signal is propagating. Here in between the device is there. So here small cavity is there. And at some particular point, okay, at some particular point, which point? So resonating frequency of the cavity, this one, and here a signal frequency. This one is about your signal frequency. When the resonating frequency of the cavity and a signal frequency is a match. So when they will match? Because when we move this particular plunger, so that a cavity size will change, and based on that cavity size, the resonating frequency change. So now we need to adjust the cavity in such a way that a resonating frequency and a signal frequency will match. So means what? If that resonating frequency match, then there won't be any output. Okay, because what happened here? So because of that matching the frequency of this particular resonating frequency and its signal frequency, so then what happened? A standing wave occur, and then your signal will absorb. Okay, signal will lose here. Okay, it will be absorbed there. So that's why across this particular cavity, no output will see. Suppose I am saying that if I just supposed to use a ray detector now, okay, now supposed to be I'm just going to, okay, detector. I'm just going to use the detector, and that output of a detector is supposed to be I have given to the CRO now. Now this is about a CRO now. That is about a display of a CRO. Okay, that is about a centralized. Now initially what we can say that there is no match of a signal frequency. So in that case, we are able to see that some sort of a signal. Okay, the condition is that here Fs is not equal to Fr. Okay, if you are not able to see here, Fs, that is about a signal frequency, and this resonant frequency is not matched. Now, if that resonating frequency and a signal frequency will match, then in that case we are supposed to get the DPO. Okay, so just like you're supposed to get that a small DPO. So that is about the signal. We say that a Fs is equal to Fr. Okay. Now we say that a resonating frequency is match here. Okay, signal frequency and resonating frequency match. It's across this detector a DP will occur. DP means what? Only either it is about a straight line, a small amplitude. Okay, either a small amplitude or a straight line there. So that is called as the DPM. Because that resonating frequency and signal frequency match, so that's why whichever the signal we supposed to be propagating through the guide through this input side here, so that will be absorbed here. Okay, we supposed to consider that it is above because it's standing wave occur, and because of that standing wave here, so power will be absorbed by the cavity when the tuning frequency, okay, resonating frequency, and your input signal frequency will be a match here. Okay, so that's this way we consider that for a given particular guide, okay, so we can say that for a given particular device, meter here, so your signal will be absorbed here, means power will be absorbed. So that's why we'll get the deep here. So at that particular deep, whenever we'll get a deep at detector, okay, on a display, so then here on this device, there is a scale, okay, there is small scale is there. So now then that particular scale will reflect you how much will be the a frequency. Okay, so we can measure it. So I'll show you that a frequency meter there. Even you can see that a practical one. Okay, so in which we have shown you that particular micro component. Okay, so now I'll show you that a frequency meter. Okay, in next lecture there. Okay, so how it will be measure the a frequency there. So we should know that at only the resonating frequency. Okay, means signal frequency and at the signal frequency and resonating frequency signal matches, then your power will be absorbed. So deep will be seen at the CRO there. So that is about a wave meter. That is about a one more component of the device. So then after that wave meter, okay, we can consider that another component. After the wave meter, there will be a standing wave detector. There will be a standing wave detector, or we can say that a slotted section with a probe carrier. Okay. After that, we supposed to use a standing wave detector. Now, how this standing wave detector looks like? Okay. Now we consider that for a given rectangular waveguide, this one is about our rectangular waveguide. Okay, this one is about our rectangular waveguide. Now, what happened here for the given rectangular waveguide? So at the wider side, this one is about a width we say. At the wider side here, there is a small section. Okay, there will be a small opening section is there. And this particular section is supposed to be called as a slot. This one is called as a slot. So that's why we say that another name for the standard wave detector is about a slotted section with a probe carriage. Okay, slotted section with a probe carriage. So here we can consider that for a given particular line, say this one is about a slot here, and this one is a waveguide now. And for this waveguide, top section of the waveguide, there is a small slot. And this slot is used or slot is designed in such a way that won't be any what we can say that reflection or there won't be any absorption of a power will be occur through the given particular a slot there. Okay, so slot is to be adjusted in such a way that so that we can insert a probe across this or in this particular slot here. And generally we say that here that probe is used to measure only the E field. Why E field? We consider that for a rectangular waveguide, now this is about a shape here. So we consider that this one is about a E component, E field component. Now here I suppose to consider that this one is about a E field component. So at the center of a guide, always there will be a maximum electric field intensity. So that's why a slot is present at the center of the this particular a guide here. Okay, this for this particular width now. And then this one is about a width, or we can say a broader side of a waveguide. This one is about a small side. This one is about a broad side of. So at this broad side of waveguide, there is a small slot is present, and through that slot, we're supposed to insert one probe, and then probe is inserted inside this particular slotted section. Now, how will it will be inserted here? Okay, so now we consider that there is a small section of a probe is there that is to be inserted inside the guide here, and then we're supposed to use for a given particular slotted section a shorting plunger here. I'll I'll draw again the how the detectors will be. Okay, and then here is some a detector diode, and this plunger is supposed to be rotating here inside the guide. Whenever we rotate this particular plunger, then depth of that particular probe will be increased or a decrease through this particular plunger. This one is about a plunger, and here we have the coaxial cable, coaxial connector, or you can say that PNC connector here, and then before that there will be some diode here. That is about a detector diode. Okay, so that detector diode we supposed to connect either a CRO or a VSWR meter. Okay, either we use this one probe to connect the CRO or to the connect to the VSWR meter. And here on this particular device, if you see that for a given particular a slotted section here, this one is about a slotted, and that slotted section is supposed to be moved through this guide here. Okay, this one, and here is small scale is there. Okay, there is small scale, and that scale is called as a vernier scale. This one is about a small scale. That is about a vernier scale. And here a knob is there so that when we rotate this knob, so your probe will be moved toward the generator or toward the load here. Either in this direction or we can rotate this direction. Okay, and here for this device, small, sorry, small this. Okay, this one is about a setup is to be corrected, and that will be your a component likewise. And this one is about your a probe now. So probe is inserted inside the waveguide. Where it is inserted? At the broader side of the waveguide, there is a slot present. Through that slot, that probe is to be inserted. And we're supposed to insert a small section of a probe. Okay, so that that particular probe is able to measure the measure the field here. Okay, now we can move this probe toward the load end, or we can say that we can move the probe toward the load end or toward the sources. We're supposed to connect this slotted section probe carriage to the after the wavemeter here, and that slotted section probe carriage is used to measure the whatever the whatever the voltage or whatever the signal is present there. So if supposed to be we are using a CRO now, on the CRO, whatever the signal detected by this particular detector diode here, this project, and that detector diode detect the signal, okay, because power is propagating. This one is about a signal, that is about a input signal. For the input particular signal, when that signal will fall on this particular probe, it will convert into form of a current, and then we are able to see the current waveform on the CRO. Generally, we say that it is to be converted in the form of voltage. So we'll get that on the CRO, given particular CRO, there will be a waveform of a signal. Whatever the 1 kilo, generally we supposed to use a 1 kilo signal, whether it will be a sinusoidal, okay, mostly for the reflex piston, it is about a square waveform. This one is about your CRO now. So at the CRO, we supposed to get the, because it is about a square wave signal, because 1 kilo signal is to be used as a reference signal. So it is V square, not a sinusoidal. So we supposed to measure that on the signal on the CRO, we able to measure the what will be the square wave here. Okay. So now when we rotate toward this end, toward the load or toward generator, okay, this one is the load now. This one is about a source now. So toward the load, so then that we supposed to say that a deep occur means we supposed to say that this peak to peak amplitude decreases or peak to peak amplitude increases. Means this slotted section, or we can say that a standing wave detector is used to measure the what will be the standing wave signal or maxima or minima of your standing wave signal there. Okay, so means we are able to find out where the maxima occur and where the minima occur, because output across the CRO on the CRO here on the CRO we supposed to say that there will maximum peak to peak or there will be minimum peak to peak. Okay, whenever we are moving toward the load or generator. So here the scale is used to measure that at what particular point or at what particular scale we are getting the maxima and a minima there. So that maxima and minima point we supposed to measure from the load end. So means from the load end means what? We supposed to rotate this probe toward this direction. Okay, this direction. So that we are able to measure the whatever the maxima and minima there. Or we can use the VSWR meter so that what will be the standing wave ratio that directly we can measure through the standing wave detector. Okay, so that is about what we can say is standing wave detector, or this one is about a slot, and that on the slot that probe is present. Okay, that tunable probe is present. So that's why the name is called as a slotted section with a probe carrier, standing wave detector, or we can say that a slotted section with a probe carrier. Now how it will work? There is a probe. This one is about a waveguide here. Okay, so this one is about supposed to be a waveguide now, and your signal is RF signal is there. Now this one is about a probe here. that probe is inserted, and that probe is connected now to the this particular probe is connected to the a detector. So now the detector will detect the signal. Okay, so likewise we have the setup likewise now. Consider that this one is about a setup here, and for this small plunger here. Okay, and then we suppose this one is about a shorting plunger, or we can rotate, or we can increase the depth of this particular a probe here through this. And this one is connected to the what you can say that it is about our device now. So likewise, we supposed to consider the bypass capacitor here. Okay, and then we supposed to use when if you are not able to consider here, just like we supposed to consider there will be a BNC connector. Okay, there is a capacitor now here, and then there's bypass capacitor is supposed to be connected to the VSWR meter or the ACR here. And how your signals are there? RF signal. Generally, what we can say that RF signals are likewise. Okay, so likewise, and then we should measure that what will be the wave or whatever the signal is propagating to the guide. So generally, at the broader side of a waveguide here, that probe is inserted. So we're supposed to measure the electric field here. Okay, what will be the E field here? So that is about a standing wave detector is used to measure the E field. So another bench component. So we can consider that a VSWR meter, because this after the standing wave detector, a VSWR meter is to be connected to your that a tunable probe, and that generally VSWR it consists of an amplifier, and that amplifier is used or it is to be tuned at the 1 kilohertz of a signal there. Okay, and if you consider that on a VSWR meter, there are the three different scale. One is about okay, so it is to be measure the VSWR, and that measured VSWR is from the A1 to a 3 dB there. Okay, so generally you consider that there are the three different scale on this display there. That is about a normal one, then a expanded one. Okay, and then another scale is about a dB scale. And then we say that here 1, 2, 3, 4, 5, 6, 7, 10 here, or we can consider here that is from the 3, then a 10 here. Okay, or we can consider that a expanded scale. Okay, so we can consider that a normal scale or expanded scale there. Are we supposed to use measure that a expanded to the 1 to 1.3 here? That is about a expanded one. Below that there is a dB scale. Likewise, again another one is about a expanded dB. Okay, so likewise, so we have the a different scales on the VSWR meter that is used to measure the what will be the standing wave, okay, or what will be the VSWR value. So VSWR value when we are getting, we need to adjust that particular slotted section probe carriage at the center where we get the maximum value, and that maximum position of the guide is to be adjusted at 1. That meter scale is to be 1, and then we supposed to find out that uh, value of the VSWR. Okay, directly there. So then because we supposed to rotate that probe and we'll get the directly what is the VSWR. We supposed to adjust initially whatever the deflection at the 1 through the gain control knob, or whatever the mode control now. Okay, voltage control knob is present on this particular device. So that's all about what we can say that is today's section. That is about a standing wave detector and a slot restriction with a probe carry. So thank you all of you. So maybe